module, you will learn about reversible and irreversible processes. Consider a system taken from its initial state I to a final state F in a thermodynamic process. Let us represent the process in a PV diagram as shown. The process is called a reversible process. If the system and its surroundings can be brought back to the initial states without causing any change anywhere else in the universe. But many natural processes are not reversible. For example, when coal is burnt, it converts to ash and carbon dioxide and in the process releases some heat. Can the process be reversed and convert ash to coal again? We observe accumulation of dust everywhere in our houses. Can the accumulated dust on its own fly away and make the house clean? Not only the processes we have just discussed, but many other processes in nature are not reversible. In fact, we can conclude that irreversibility is not an exception but a rule of nature. Why is it so difficult to find a reversible process in nature? Let us consider a steady flow of liquid through a pipe of variable cross-sectional areas. As the liquid flows through the pipe, it may have different speeds at different points. Let the speed of the liquid at A be V1. When it moves from A to B, its speed increases, say from V1 to V2. The process is reversed and the speed of the liquid decreases from V2 to V1 as it moves from B to C. Hence, the process is almost reversed. The complete reversibility of this process is possible only if the liquid is non-viscous. This means the speed of the liquid is the same at A and C only if the liquid is non-viscous. However, in real life, this does not happen. Because of the dissipative effects due to friction, viscosity, etc., complete reversibility is not possible. As we can only minimize the effects of dissipative forces and cannot completely eliminate them, most processes in nature are irreversible. There is another cause for irreversibility that arises due to the system passing through non-equilibrium states. When the system is passing through non-equilibrium states, we cannot identify the intermediate states of the system precisely. As a result, we can't identify the correct path through which the system has passed, while changing from the initial state I to the final state F. Hence, reversibility of the process is very difficult. However, we have defined a quasi-static process as an ideal process that always passes through equilibrium states. Now, we can write the conditions for a process to be a reversible process. For a process to be reversible, it must be quasi-static. And there must be no dissipative effects. Like a quasi-static process, a reversible process is also an ideal one. For example, Consider an ideal gas in a container with a frictionless movable piston. A quasi-static expansion or compression of this gas is an example of a reversible process. According to the second law of thermodynamics, we cannot construct a heat engine with 100% efficiency. So, what is the maximum efficiency of a heat engine? If a heat engine working between two temperatures, T1 and T2, passes through idealized reversible processes, then the heat engine achieves the highest efficiency possible. You have now reached the end of this module. In this module, you learned that a process is called a reversible process if the system and its surroundings can be brought back to their initial states without causing any change anywhere else in the universe. For a process to be reversible, it must be quasi-static and there must be no dissipative effects. A heat engine based on idealized reversible processes achieve the highest efficiency possible.